In this lecture and the next, we are going to look at linear difference equations. Now, what you will find is that the methods of solving these difference equations are very similar to what we'll do when we come to differential equations. Difference equations look at discrete time, whereas differential equations deal with continuous time. So let's first look at the first order linear difference equations. So let's consider the difference equation a0yt plus 1 plus a1yt is equal to 0. Because it's equal to 0, it's homogeneous. In operator form, we can express this same equation as a0e plus a1 all times y to the t equals 0. So we rearrange the original form and we get yt plus 1 is equal to minus a1 over a0 yt. And we allow b to be equal to minus a1 over a0 so that we have yt plus 1 is equal to byt. Now what we need is an initial condition. So let's suppose that we're given at time t equals 0 that y at time 0 is equal to c0. So that means that y in the next period, y1, remember we've got y0 here, this would then be y1 because t equals 0, so we get y1 is equal to b times y0, which y0 being c0 gives us y1 equal b c0. So then y at time t2 is equal to b times y at t1, which is simply b times b c0, which is b squared y0 or b squared c0. And thus, in time period 3, we get that y3 is equal to b to the power 3 times c0. And more generally, we find that at any given time t, yt is equal to bt times c0. So that if we go back here and we put in t equals 0, we get b to the 0 times c0, and that's equal to c0 because b to the power 0 is simply 1. So this is a completely general solution of the difference equation, and that solution is given by this expression here. Now, we can look at a number of cases. In fact, we have to look at a number of cases. The first is that we assume c0 is greater than 0 and that b is greater than 0. So if b is greater than 1, we see that raising b greater than 1 to some power t and multiplying by t results in yt approaching infinity as t approaches infinity. If b is equal to 1, then yt at any given time is equal to c0. So yt equals c0 for all t. And if b is less than 1, then yt declines as t increases, and at the extreme, yt approaches 0 as t approaches infinity. Now the second set of cases has b less than 0. Since b is equal to minus a1 over a0, and a1 and a0 are both identified as being greater than 0, then b will alternate in sign depending on t. If t is positive, then yt is positive. If t is negative, then yt is negative. So what happens is we get oscillations. So if t is positive, yt is positive. If t is negative, yt is negative. So if b is less than minus 1, oscillations of yt explode as t increases. So in other words, yt will oscillate back and forth being a positive and a negative number, but it will explode as t increases. If b is equal to minus 1, yt alternates between plus c0 and minus c0. And if b is greater than minus 1, but it has to be less than 0, then the oscillations dampen with yt approaching 0 as t approaches infinity. And we can illustrate these 6 cases in these following diagrams. So here we have yt on the vertical axis, t on the horizontal axis. We pick a point c0, c0 being greater than 0, and assuming that b is equal to 1.2, we plug that back into this equation here, this general solution, and we find that yt is increasing with time. If b is equal to 1, C0, yt is equal to C0 throughout any period in time, and it becomes a straight line. If b is less than 1, but remember it's still positive, let's say that we pick 0.6, then what we do is we get a declining yt as t increases until as t goes to infinity, yt will go to 0. Now if b is negative, less than 0, then we get oscillations. So if b is minus 1.2, we get oscillations that explode. We see that here. If b is equal to 1, then the oscillations go from C0 to minus C0 to plus C0, minus C0 throughout. And finally, if b is negative but greater than minus 1, say negative 0.6, then we see that these oscillations dampen until yt approaches 0 as t approaches infinity. So what happens if we have higher order linear difference equations? So let's look at a second order equation. And the general equation in operator form would look like this. A0e squared plus a1e plus a2 all times yt equals 0. Or we can say that a0 multiplied by yt plus 2 plus a1 multiplied by yt plus 1 plus a2 multiplied by yt is equal to 0. Now recall how we wrote the first order difference equation as this, and we could rewrite that as e minus byt equals 0. Well, here we have this equation in operator form, and it can be rewritten as e minus x1, e minus x2 all times yt, or e minus x2, e minus x1 times yt equals 0, where x1 and x2 are roots of what is called the auxiliary or characteristic equation, where a0 x squared plus a1x plus a2 is equal to 0. Notice the how the characteristic or auxiliary equation looks very much like this general equation in operator form, but we've just substituted these e's with an x. So if yt is a function of t is found that satisfies this equation, it also clearly satisfies these equations here, this equation here. So if yt is equal to gt, is found that, so if we find yt is a function of gt that satisfies this equation, notice the difference here, x1 up here, x2 here, then it also clearly satisfies this equation for the simple reason if this is 0, then this part is 0, and this whole equation will be 0. So from the results of the first order linear difference equation, we found that the solution to e minus x1 yt equals 0 gives you yt k1 x1 to the t, where k1 is a constant. And we also found from that same one that solution to e minus xt yt equals 0 gives us yt equals k2 times x2 raised to the power 2, where k2 is a constant. So then a general solution to the second order difference equation is given by yt equals k1 x1 to the power t plus k2 x2 to the power t. Note that x1 and x2 are solutions to the characteristic or auxiliary equation up here. All right, now what we need is a pair of initial conditions at t equals 0 and t equal 1 before we can solve this particular equation and determine what k1 and k2 are going to be. So first let's begin with these two roots, x1 and x2. So generally, there are two distinct roots to the auxiliary equation. Two distinct roots to the auxiliary equation, and it's given by our quadratic formula for finding x in the quadratic function. And you'll recall that that's given by minus a1 plus or minus the square root of a1 squared minus 4a0 a2 divided by 2a0. You'll just have to review that quadratic formula if you're unclear about that. So let's let the initial conditions be that y0 equals c0 at t0, and at t1 that y1 equals c1. So then we get these equations. So what we're going to do is we're going to plug in t equals 0 here, and we get x1 to the 0 is a 1, x2 to the 0 is a 1, and we get k1 plus k2 equals c0. If we put a 1 here where the t is, then we get x1 k1 plus x2 k2 equals c1. So c0 and c1 are determined from the initial conditions, and x1 and x2 are determined from the values of a0, a1, and a2. So unique solution to the two equations can be found as long as the determinant, and now we express this in matrix form. So the determinant of the matrix 1, 1, 1, 1 here, and x1, x2, x1, x2, as long as that's not equal to 0, then this implies that x1 is not equal to x2. So if we have the condition that x1 is not equal to x2, then that solution here, this general solution, will hold, and we can find an answer. So if c0 and c1 are equal and they equal 0, we get a trivial solution that yt is equal to 0 for all t. So that's not of interest to us. So we want to look at the types of roots that we have. So second order equations, distinct roots. So here is an example. So yt plus 2 minus 8yt plus 1 plus 12yt equals 0. Given initial conditions that y0 equals 57, y1 equals 334. In operator form, we get e squared minus 8e plus 12, all in brackets, times yt equals 0. The auxiliary equation is x squared minus 8x plus 12 equals 0. We can find that x minus 6 times x minus 2 is equal to 0, so that means that the solution is that x is either 6 or 2. So we have two distinct roots, 6 and 2. As before, we guess this solution, so we plug in the x1 here and the x2, and we get k1, 6 to the t, plus k2, 2 to the power t as well. So at t equals 0, we're given these initial conditions, so k1 plus k2 equals 57, and at t equals 1, so we put a 1 here, then we get 6k1 plus 2k2 is 334. We solve for k1 and k2. We find that k1 is 55, k2 is 2. Therefore, yt is equal to 55, 6 to the power t, plus 2 times 2 to the power t, which gives 55, 6 to the t, plus t2 times t plus 1. Yt plus 1 here because of this 2. So this is 2t plus 1. Now, there are two complications here. One is if we have multiple roots, in other words, x1 equals x2, and second, if we have complex roots. So when you think of complex roots, think of the square root of -1, which gives us an imaginary number, as we'll see below. So with multiple roots, let's look at this example here. Yt plus 2 minus 10yt plus 1 plus 25yt equals 0. We have initial conditions that y at time 0 is 3, y at time 1 is 25. We construct the equation in operator form, e squared minus 10e plus 25 all multiplied by yt equals 0. We find the auxiliary equation, which is x squared minus 10x plus 25 equals 0, which gives us a root of x1 equals 5 equals x2 equals 5. So for multiple roots, the general solution is modified as follows. Yt equals k1 x1 to the power t plus k2 times t. We add this t in here, times x2 to the t. So at t equals 0, we get k1 plus 0, because this is now a 0, equals 3. This is our initial condition. And we get 5k1 plus 5k2 equals 25. Again, our initial condition for t equals 1. And that gives us this solution here, that k1 equals 3 and k2 equals 2. So then the general solution is given by yt, 3 times 5 to the power t plus 2 times t, 5 to the power t. And we get basically that yt is equal to 3 plus 2t, all multiplied by 5 to the power t. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.